Hi everyone. Today we'll be presenting our research on battery-aware search and rescue with drone swarms. So our work addresses key challenges in using drone swarms for search and rescue operations, particularly focusing on battery life limitations and coordination challenges. As we can see in the background image, we're exploring how multiple drones can work together while managing their power constraints effectively. Let me begin with a real-world case study that demonstrates the need for this technology. In October 2020, Cambodia and Vietnam faced devastating floods and landslides that affected millions of people. During this crisis, drones proved to be invaluable rescue tools. This aerial image shows a hydropower plant completely covered by a landslide in central Vietnam, highlighting how multiple drones can access dangerous areas that would normally be impossible or extremely risky for human rescuers to reach. However, current drone technology faces major limitations in search and rescue operations. Firstly, battery life is severely limited, as shown in this graph correlating flight time with battery capacity. Even as the battery capacity increases, it gets to some limiting constant having to do with the battery weight. Second, we face significant coordination challenges, illustrated here with different drone swarm control architectures, from centralized to fully autonomous. Lastly, there's a crucial problem with recharging drones in the field, as they typically need to return to a fixed base station that can be far from the area of interest. To address these limitations, we propose a two-pronged solution. The first component involves battery-aware adaptive potential fields for intelligent UAV path planning and exploration. This ensures drones can effectively navigate while considering their power constraints. The second component utilizes mobile wireless power transfer stations, a novel technology which allows drones to recharge in the field without returning to a fixed base station, which can significantly extend their operational range. The principles we're developing here extend well beyond the search and rescue applications and have broader impacts. For example, in the field of agriculture, these systems can enable continuous crop monitoring over large regions. For infrastructure inspection, drones can effectively inspect long distance assets like pipelines and power lines. And in environmental monitoring, our approach would allow drones to collect data in remote areas for extended periods, all while maintaining optimal energy efficiency. Now let's dive into the actual technical details of the framework and methodology. So our implementation required tackling four key engineering challenges. First, developing the battery-aware potential field system that dynamically adjusts based on battery levels. Second, implementing a simulation environment with a realistic battery life heuristic for the drone swarms. Third, integrating mobile wireless power transfer stations. And then finally, optimizing swarm coordination to balance exploration and recharging efficiency. Our battery aware planning system uses a three-tiered approach. At the top level, we have battery awareness, where UAVs prioritize routing back to their charging stations based off of their remaining power. In the middle, adaptive potential fields dynamically adjust based off user-defined areas of interest for searching. And at the bottom, we implement optimized exploration algorithms that balance efficient coverage with energy conservation.
Yeah, so looking at kind of just like a basic potential field and explaining what that means. Potential field is something that guides the robot towards local minima and is given by that attractive potential. And so then the robot will get a force that pushes it in the direction of the lowest potential. Um, And then on the other side, for obstacles, we don't want to run into obstacles. So they have a repulsive potential given by that equation where the drone will get a force away from the obstacle to guide it around any potential obstacles. And then kind of putting those two together, we can see a potential field on the left that is high where there's an obstacle and low where there's where we want to go. And then that gradient force on the right can be seen so that the drone will be pushed away from the obstacle and towards where we want to go. Yeah, and then for us, we wanted to add a couple more components to this potential field for our scenario. So first off, we wanted to add battery awareness, and we wanted to be able to balance our exploration and getting back to a charging station and try to explore on the way back to a charging station. And then we also wanted to never run out of battery. And so then our potential for a drone became a piecewise function, one where it's kind of in an exploration phase, and the other when it's retracing its steps back towards a charging station. We also wanted to add an area of interest, so where we wanted to search for survivors. And so this gives an attractive potential to the drones to guide them towards where we think survivors might be. And then we wanted to add repulsive force for other drones and for places that we've already explored. And so those repulsive forces are given by the equations there. And this will help guide the drones into finding new areas and looking for survivors where other drones have not already looked. And then for the battery awareness piece, we wanted to, we can see that the parameter on the left, kbat is equal to 10. We kind of explore and go around to the area of interest, which is given by that green triangle. And then for kbat is equal to 100, we don't actually get to the area of interest, but we can see that the drone is exploring around on the way back to its charging station. And then a little bit about the backtracking algorithm. We want to be able to backtrack to a charging station. And to do this, the drone needs to follow a known path so that it doesn't run into any obstacles and it takes a known distance back to give that threshold. And so to do this, we keep track of the drone's path in a tree that all leads back to the route, which is the charging station. And so in one example simulation in the bottom right, you can see the drone kind of wandering around exploring, but it creates the tree of known positions on the left. So it guides itself back in an optimized way towards the start charging station.
So I'll be talking about the mobile wireless power transfer stations. So in an unknown environment, drones exploring an environment would die after a certain amount of time, like when their battery runs out. So introducing these stations would allow for charging in the field. So these stations can be like a car with a wireless charging pad on top of it. And we work to ensure that these can dynamically recharge drones out in the field. We optimize these WPT movements to support all of the drones in the search and rescue operation and to ensure that there is a continuous mission progress as time goes on. So this is our scheduling algorithm, and essentially we take in all of the drones and their battery information and we categorize them into two different categories. The first categories are drones that are at the frontier or that are exploring unknown environments, and they have sufficient battery to do this exploration. And the second category are drones that need to be recharged that are below a certain threshold of battery, like let's say 30 or 40%, and they're trying to find a recharging station. So given these two categories, we want to ensure that no drones die, or we try minimizing the amount of drones that reach a battery level of 0. So we assign WPTs to all of these drones in this category of drones that need to be recharged, and then we tend to the drones that are at the frontier. So these frontier drones are usually far out, away from the WPTs, so the WPTs move towards them, and whenever these frontier drones need to be recharged, the WPTs would be nearby in order for them to recharge quickly and go out exploring for more survivors. So in order to constrain the WPTs and also mimic real world environments, we used a few math techniques. So in order to define the path that a WPT can move, we looked at roads that can be found anywhere. So they're usually a line or a curve. So you can, in our simulator, you can input a sine or a cosine or any function, and then we will create a convex hull, and then we can transform it anywhere onto the unknown environment in our simulator. So this allows us to simulate any exploration environment that has like a road or a dirt path that a WPT can move on. And taking all of this, here are our results. So in order to measure the success of our algorithm, And our approach, we looked at three measures: the success rate, or the percentage of survivors found. We want to obviously maximize this. The recharge optimization, so the time spent in recharging procedures versus total mission time. And we obviously want to minimize this. And then responsiveness, so the total time to locate all of the predefined survivors in the simulation. So this is a visualization of our algorithm working. So on the left is just a random walk where the drones, indicated by the different colored paths, move randomly in an environment, and on the right is our algorithm. So you can see that our algorithm has a more systematic approach, and you can see that there are some emergent behaviors that are shown where it has like a grid search pattern of sorts, and also the drones kind of take their own section of the environment to explore. And also, in the next slide, we have some quantitative results. So we averaged out over multiple runs our method and compared it to a random walk method, and these are our statistics. So our method, you can see, has found more of the survivors, around 78%. We have covered more of the unknown environment, 71%, and in the minimum battery column, you can see that the lowest battery level that our drones got to was 33%, while in the random walk, the lowest battery level was 0%, which essentially shows that drones were dying if they just were randomly walking throughout the environment. So those are the main metrics that we looked at, and there are two others on the right, and I will pass it off.
Yeah, so what we want to do in the future, and what we hope to see, is that by varying our APF parameters, like the attractive potential and the battery or the repulsive potential, we want to see how these parameters have an effect on our success rate, the recharging, and the responsiveness of the drones, and how many survivors that they can find. And so from this, we're going to optimize the balance of the parameters to find the maximum number of survivors in some realistic scenarios. And so this will allow us to determine the balance and effect of our battery awareness, and it'll allow us to determine the effect of a moving WPT compared to maybe a stationary one. And then with this optimized APF, we were going to compare to other solutions such as random walk, as you saw before. So these give us our key takeaways of our battery aware path planning that optimizes our energy efficiency and allows us to explore efficiently with respect to our battery and our recharging. It gives us the idea that the mobile WPT stations allow for better coverage throughout the drones as opposed to a stationary charging station. And it shows that we have enhanced efficiency across our APF compared to a normal APF or a random walk, with more survivors found and faster missions. And these are some of our sources for the slides.